Algebra 1, Chapter 7.6, we're going to talk about exponential growth and decay, guys. But we're not talking about the parent-family child. We're not graphing these ones today. So, exciting. What we are doing, though, is we will be using an exponential growth or decay equation to represent real-life type of situations. Now, obviously, when the book says real-life applications, we contrive it just a little bit. But yes, this can model stuff in real life. Remember, exponential equations start low and go higher, or start higher and go lower, right? That's an exponential equation. So, what are some things in real life? Well, money. Money is near and dear to all of us. We all want lots of it, even though necessarily more of it doesn't make you happier. So, it's one of those things that we kind of need in life to, buy the things we need, buy some things that we want. But here's the thing about money. Most of us, okay, probably right now, most of you guys don't even know what a job is. Some of you guys might. And you guys probably aren't even thinking about the fact that at some point in your life, you're going to start working for a really long time, and then eventually you're going to want to stop working, called retirement, right?
401k.
And you guys are going to want to be able to live without having to work. You're going to want to be able to do all those things you couldn't do because you had a job. So, most of your parents have 401ks, investing their money. This is how exponential equations work. You start, guys, exponentially with a small amount of money. You may start with a couple $100 and you start to invest it. Well, that money will grow. It grows slowly at first. But here's the thing. 10% of 100 is only $10. 10% of 1,000, though, is 100. It's more. So the more money I have, or more of something I have, the same percentage of it gets you more. So if you're growing by 5, 6, 7%, the more you have, the more you're going to get. And the more then you have, then the more you're going to get even more. And that's why money grows like this, exponentially. On the flip side, guys, you buy a car, and your car might cost $20,000 to $30,000. But within that first year, it drops $5,000 to $6,000. The second year, third year, fourth year, it's lower and slower decay. You lose more money your first year than you probably do in years 7 and 8. Probably 7, 8, 9, and 10 combined. Because a car can only lose 10%. 10% up front is a lot, but as the price goes down, 10% is not as much. Populations, guys, grow exponentially. If I inherited an island that had nothing on it but plants and stuff, and I introduce a set of bunnies onto this island, and I come back a year later, am I still only going to have 2 bunnies? I'm going to probably have a whole bunch more bunnies. We're going to assume that we're putting a male and a female on there. And because we know bunnies multiply, and the more bunnies you have, the more bunnies you get, and the more bunnies then, the more bunnies. Populations are the same way. Populations grow at an exponential rate. Or they actually can decline at an exponential rate. People are leaving a certain town. The town is losing people because of jobs, the economy, or there's some other draws someplace else. Radioactive material has a radioactive half-life, which means half of the amount is there than original. But every time you do that, you keep cutting it in half. Yeah. So it all comes down, guys, to this same equation, whether I'm talking about growth or decay. In the book, they separate the 2 different sections. I'm going to say, hey, it's the same equation, but the only thing that differs is that I'm adding the percent increase or subtracting the decrease. So what we have here is we have an equation of y, which is our final amount, times a, which we're going to call the initial amount. So we have the initial amount, 1 plus or minus r, which is the rate. Now, I'm going to tell you this. If it's 5%, we're not putting a 5 in there. We're using 5% as a decimal, which means, so 5% is equal to 0.05. I move the decimal place. That was, here, 2 places to the left. 1, 2. And that's why you get that. So the rate as a decimal. So the rate as a decimal, and the exponent is t for time. Now, if something is growing every 10 minutes, or in minutes or hours, so in hours, times in hours. If it's per day, then it's in days. If every 10 minutes, then you need to break it into 10-minute segments. Stuff like that. So time is dependent on your rate. You get a 5% increase per what? Year? Then times in years. Now, I say it's plus or minus. Again, if it's a 5% increase, I'm adding 1 plus 0.05. If it's a 5% decrease, it's 1 minus 0.05. And I'm going to highlight why it's a growth and why it's a decay as we do our problems. Are we ready for the problem? Yeah. Oh, wait, I got one more question. What is 0.8% as a decimal? It's 1, 2, so 0.008. Still moving it over 2 times. So be very careful on that one. Okay. So, here's a cool radio station that has a prize contest. It begins with a $100 gift card. Once a day, a name is called. That person has 15 minutes to call back, or the prize will increase by 2.5% for the next day. So you only got 15 minutes to call them back. Say, hey, that's me, that's my name. And then you have 2.5% increase for the next day if no one claims it. I want you to write the equation that represents the amount of the gift card in the dollars after T days with no winners. Because as soon as someone wins, it starts over.
How do they know if it's you?
B, how much will the gift card be worth if no one wins it after 10 days?
Where is the gift card for?
So, is this money getting larger or smaller?
Bigger.
It's getting larger. So this should be an exponential growth equation. So I am going to write down, guys, the initial formula of what it should look like. And that should be the 1 plus r formula. Yes? And once I've written it down, because we haven't done this in a while, we haven't had to write down formulas before we used them in a while. You should always do it. Start plugging in information. We don't know why. Why is what we're looking for. How much is the initial amount?
100.
100. And 1 plus
2.5. Nope. Oh, 0. Oh, wait.
2.5%. 0.025 to the t, because it's after t days. We don't know how many days go by, right? Now, I don't like this. I think this can be put together. Would you guys agree with that? So, y equals 100 times 1.025t. And that is the equation to find out how much money that gift card would be worth after t days. Now we have to figure out 10 days. So what do you do?
Put the equation is right. 10 for t.
Put it 10 for t. Y equals 100, 1.025 to the 10th power. You guys probably have to take a calculator out. That's fine. What is 1.025 times 10 to the 10th power? And then multiply that by 100. No, it's not times 10 times 10 times 10. It's 1.025 times 1.025 times 1.10 times. Right? That's what definition of exponents do?
Yeah, 1.025 times 1. Yeah.
Yes. 10 times. Or put in, use the exponent button.
Wait, so you didn't take that answer times 100?
Then take that answer times 100 times 100.
That's like 100.
Times that by 100. 128.01. Yes, that is the answer. This is an exponential equation. It's a base to a power, yes? And this base, which is 1.025, is that bigger than 1 or less than 1? So therefore it's growth. And if I multiply it to itself, in this case 10 times, I'm going to result in a larger number. That larger number gets multiplied by 100. I get $128.01. That gift card after 10 days is $128. It gained a 28% increase in 10 days. That's pretty good. Now, I got a question. How much was it after day 1?
Just put 1 for t.
Yeah, if you put 1 for t,
It's just 100 and...
2.5, right?
Yep.
So day 1 is 102.5. That increased how much?
$2.
$2.50 in the first day. So if that's the case, 10 days later, wouldn't I just have to do 2.5 times 10 and add it in? What's 2.5 times 10?
28.01.
No, it's 25, or 2.5 times 10.
25.
It's 25. Do you notice that if I thought that the first day's increase was the same as the increase always,
You'd be wrong.
I'd be $3 off in the first 10 days.
So then 20 days, you're $6 off.
I'm actually going to be more off
9?
because
Like over time, it gets bigger.
it's getting bigger faster. And so therefore, being off just a little bit on these equations will definitely throw your numbers off. Okay, guys, let's talk about an exponential decay problem. Here's a population problem of Campbell County, Kentucky. It has been decreasing an average rate of 0.3% per year. Not really that big, right? In 2000, its population was 88,647. I would like you to write an equation to represent the population since that year's population in 2000.
Yeah, y equals...
So what does this mean? It means that year 2000 for our t values is where it begins. So 2000 represents year 0, time 0. T equals 1 is 2001. 2 would be 2002, and so on. You guys agree with this? So please, write me the equation. I'll help you guys out.
Is it 0.3 for... Oh, is it y?
I gave you the equation, you fill it out.
We're up with 8.
So, A, the initial amount is 88,647. And 1 minus, because we're going to lose percentage. But 0.03, guys, 0.3, sorry, I have to move the decimal 2 places over. It ends up being 0.003. So I'm actually 0.003. 1 minus that to the t power. But what happens when I subtract 1 minus 0.003? I end up with 0.9 0.997t. And is 0.997 bigger than 1 or less than 1? It's less than. So therefore, it's decay. It's losing value. Now that we have the equation written, we now can plug in 2018, which would have a t value of 18. 0.997 to the 18th power equals, and times that by 88,649. So you end up with 83, comma. So what do we get when it's 88,647 times 0.997 to the 18th power? It's still 83, comma. Be tough to use your calculators, guys. The things that you bring every day to school, things you brought to class every day. What's that? 880? 0.2 or something like that. 980. Okay. First of all, guys, it lowered. It's 83,980.19 or 0.2. Do we really have a fifth of a person? No. So, remember, this is a roaming number. This is something that's like an approximation. So in this case, I would just round down and would have said, hey, the population will be 83,980 people in 18 years. It only loses about 5,000 people. That's not too bad in 18 years. Now, that's bad if I was an urban planner and I was trying to maybe do some development of the area and I want people to actually be attracted to the area, but the trend is I'm still losing people. Okay? So, I'm not saying every one of us is going to go out and do equations like this in real life, but there are certain jobs where you're going to use these as models to say, is something that I'm doing viable or not? The last thing we have to talk about is compound interest. Guys, compound interest is more on actual money things like making a payment on a mortgage or a car payment. If you do that, the more times you make a payment, the quicker something is paid off. If you have options, guys, when you guys eventually get older and possibly have a house or a car payment, if you're able to make bi-weekly payments, so every other week, you could cut off several months of payments just by paying the same amount you would have for the full month, broken into two pieces. It's because what they're doing every time we compound interest is basically evaluate either how much interest are we going to give you or how much interest is not being charged every single time we do it. So the more often that happens, the less money, because you're making the payments or you're getting money, it'll grow then, it makes it go faster. And we're going to see that in my example that we have coming up. So, they changed some things around here. A is now not the initial, it's the final amount. P is what they call the principal or the initial amount. R is still your rate as a decimal. T is still time, usually in years. But N, there's two N's in this thing, and that is the number of times your interest is compounded. How many times is your interest compounded? So, I have a couple examples down below. It's not always going to be just these ones. But if you see something like it's compounded yearly or even annually, your interest is compounded how many times a year? If something happens yearly, it's happening how many times a year? Once. If it's happened monthly, 12 times. If it's daily, assume no leap year, 365. And if it's weekly,
7.
52.
Wow.
Are there 52 weeks? I think it's 52 weeks. We also could be, quarterly. We could be semi-annually. All of those things could come up. So, guys, we're going to learn the power of compounding interest. Your GMA decides to give you a sweet gift for your 15th birthday party. Shh. She plans on giving you $10,000. But, hey guys, listen to this as a catch. The catch is you have to invest it until you are 65 years old. Basically, Grandma's like, I'm going to set you up for your future. Now, so the both of you go check into a few banks. I want you to find the amount of money you will have received when you turn 65 if each of the bank promises a return of 5%. In the real world, guys, there are no promises on money markets, 401s, and all of that. But typically, 5% is a good rate to get a return. So let's say the bank guarantees this one. Which bank should you choose?
B.
They're all the same.
Bank A, and we're going to figure this all out. Bank A compounds your interest yearly. So once a year, they're going to check how much money's in there, and they're going to give you interest for it. Bank B is going to compound it monthly, and Bank C is going to compound it daily. So let's find out who's got the better deal. Guys, how many years does it take from 15 to 65?
100.
50.
Oh my God.
Wow.
Guys, 50 years it takes, so that's how long your money's going to sit in every bank. If your compound equation will be A equals P times 1 plus R over N to the NT, right? So those are some things that I should write down so I don't have to think about it later. But now, let's start filling it in for each bank. Bank A. Bank A says, I'll take your $10,000. I will give you the 5% or 0.05, but I am only going to compound it how many times? Once per year. Do you see how I put 1 in for N?
Yeah. Now you got it.
Now, what's 0.05 divided by 1?
0.00.
What's T times 1? It's T. So therefore, the 1 makes it a very simple problem like you just did. Do you see that how I can combine those up really easily? And now I can plug 50 in for T. Take your calculator out, guys. What's 1.05 to the 50th power and times that by 10,000? As you're working on that, Bank B says, I'm going to take your money. Sorry, here we go. A, 10,000 bucks, right? I am also going to give you the 0.05 or 5%, but I am going to compound that interest 12 times. So that's 12 divided by 12 and then 12t. Now, okay, well, hold on. We got an answer for part A. Bank A wants to give you 114,000. 673 point. Okay, we'll just put it as 99. So they want to give you 114,000. Grandma just gave you $114,000.
What?
But we can live to 65.
We're assuming everything's fine. Okay? That sounds like a lot of money. We're going to bank A, right? Now, what we need to do now is we need to figure out what these other banks are going to give us. 1 plus 0.05 divided by 12 doesn't seem like a really nice number. I'm going to leave it for now like that, but I need to do 12 times 50. What's 12 times 50? It's 600. So I'm going to cross it out, put 600, okay? That doesn't look like 600. Okay. Now, to put this on my calculator, I need to do this part first. So take 0.05, divide by 12. 0.05, divide by 12. Add 1. Take that number on your calculator and raise it to the 600 power. And now multiply that by 10,000. And what do you end up having? 121,193.83. She gave you at Bank B $7,000 more. Just by compounding the interest 12 times more a year.
I said B, so I'm not. Let's use
See, guys. Oh, that's too many. 10,000 times 1 plus 0.05 over 365 to the 365 times 50. Whoa, what's 365 times 50? I don't want to use that. So I'm going to cross it out and use. What do we get? It's a lot of times being compounded because you're doing this every 365 times a year. What is 365 times 50? 18,250. You're in the lifetime of this loan, your money will be compounded 18,250 times. So, let's go through this one. Take 0.05, divide it by 365. Plus 1, bring that number to the 18,250 power, and times that by 10,000. It equals 121,804.08. That's what I get. Does anybody else back that up? Okay.
I guess B, that was close.
Guys.
Is that right if it's 600 for the first one, 18,000 for the second one?
Because if it breaks down smaller, it takes more to make it up. Guys, Bank C would be the best because the more times you compound something, the more value you will get. Homework is page 434, 4 through 10. Have a great day.